Good morning, champ. Today we're putting a spin on hydrostatics, literally. Ever wondered how to make a perfect parabolic mirror using liquid mercury? Just spin it. When a liquid rotates steadily, its free surface naturally curves into a paraboloid. That's the exact shape used in reflecting telescopes. In this episode, we'll derive that shape from first principles, find the rotation speed needed for the mercury to touch the rim. Let's start with the physics. In steady rotation, every tiny bit of the liquid moves like a solid body. Same angular velocity, no shear. The forces come from two sources: gravity downward and the outward centrifugal effect of rotation. At each point, pressure gradients must balance these accelerations. That gives two relationships, one radially outward and one vertically. The radial balance says the rate of change of pressure with radius equals RHO times omega squared times R. The vertical balance says the rate of change of pressure with height equals minus ROG. We integrate the first one with respect to radius, holding height fixed. That gives pressure equals 1/2 rho omega squared R squared plus some function of Z. That function captures the vertical hydrostatics. So we apply the second balance. Partial P over partial Z equals minus RHOG, and integrate again. The function becomes minus ROGZ plus a constant. Combine the two pieces, and the pressure field inside the spinning liquid becomes 1/2 rho omega squared R squared minus rho GZ plus C. Now let's find the shape of the free surface. Along the surface, the pressure equals the surrounding atmospheric pressure. At the axis, where R equals 0, the surface height is Z0. Plug that in to determine the constant and subtract the two expressions. The result is Z of R minus Z0 equals omega squared R squared divided by 2G. That's it. The free surface is a perfect paraboloid of revolution. This shape doesn't depend on density at all, only on gravity and how fast we spin. Spin twice as fast and the curvature quadruples. Next, volume conservation. The total amount of mercury in the dish stays the same. So, even though the rim rises, the center must dip just enough that the average height remains what it was before spinning. Mathematically, that means the average of the surface profile equals the original flat height, h0. Integrating across the dish gives Z0 equals h0 minus omega squared R squared over 4G. The center drops by that amount, while the rim rises by the same amount. The surface literally pivots around its average level. Now, when does the mercury just reach the lip of the dish? At that instant, the rim height equals h rim, the dish edge. Substituting into the parabola equation gives h rim equals h0 plus omega squared R squared over 4G. Solving for omega gives 2 over R times the square root of G times the difference, h rim minus h0. So that's your critical rotation rate. Spin any faster, and the mercury would overflow. The rotating mercury forms a paraboloid automatically. No machining needed. The faster you spin it, the deeper the center dips, and the higher the rim climbs. When the surface finally touches the rim, we know exactly how fast we're spinning. 2 divided by R times the square root of G times the freeboard difference. Notice how density never entered the surface shape. It affects the pressure, but not the geometry. That's pure fluid elegance. Motion and gravity balancing perfectly. So champ, that's how you turn mercury and motion into a perfect mirror. A spinning dish gives you geometry straight from physics. Until then, keep your mind sharp and your equation smoother than mercury.